we have derived the equation of motion for the base excitation of a force vibration of a single degree of freedom system. So now let us take a look at how is the response. I think this one, it has been shared before, how this response are very similar to the fixed base. Okay, the main difference here is the variable. Instead of having it in terms of x, it's actually z now, and the angle, instead of phi, we use chi. And here, if you actually look at it, if you have a steady state absolute motion of the mass, so you can actually solve for your x, z, and y. Okay, and so here, if you actually look at if you want to actually derive the equation, okay, you can refer further in the notes, but this is the relationship between x and y after we rearrange the terms just now, and we now express it in terms of x and y. And there is an important terms that we use here, which is what we call displacement transmissibility. So displacement transmissibility is basically, you can see here, is actually the ratio of your output, which is capital X, okay, over input amplitude, which is capital Y. So you can actually get the phi, okay, from this equation, okay, in terms of the variables as well. Okay, so if you actually look at the response, it's quite similar to the fixed base. In fixed base, we don't call it displacement transmissibility. Okay, in fixed base, it's actually an amplitude ratio. You don't have x over y, but you have x over static deflection. So previously, if you remember, in fixed base, you have x over the static deflection, okay, which is your f naught over k. Okay, and we call it amplitude ratio. But the figure is quite similar, yeah. So it's quite similar to this base excitation, where if you increase damping, so you can see this one is actually increasing damping. So when you increase your damping, okay, if you look at the peak here, it will actually go down for increasing damping. Okay. So you can see this line here is 0.05, but the bottom graph here is actually 1, and it's the same, it's skewed to the left a little bit. Okay, so it's not exactly at r equals to 1. Okay, it's slightly skewed a little bit. And you can see that at a specific number, r is equals to root of 2, there is kind of like a deflection point there, but basically your displacement transmissibility is less than 1. So along this area, okay, you can see that your TD is less than 1. Okay, so the phase angle, there is also kind of like an inflection point here, but it's shift a little bit. Okay, last time it was at 90 for fixed base, but for this base excitation, it shift not at one point, but it at relative different point depending on your damping, okay, or zeta. All right. Okay, so maybe you can recap. I can recap here. Basically, when your R is greater than root of 2, just now we have seen that your TD is less than 1. The value of TD equals to 1 for all values of zeta at omega or r, okay, equals to root of 2. Okay, the value is fixed at 1. So that is a very important conclusion there when we look at the graph. Other observations from the graph as well, when your r is less than root of 2, smaller damping ratio leads to larger values. Okay, when it is greater, smaller damping lead to smaller values of TD. Okay, you can actually estimate your r value. Okay, it attains the TD is at maximum for zeta less than 1 at a frequency ratio of, okay, which is also what we call r at this value. Alright, so there is another, other than what we call displacement transmissibility, you can also calculate the force transmitted. Okay, how much force is being transmitted, yeah. So force transmitted to the base or the support due to the reactions from the spring and the dashboard. So you can actually determine the force, and you can see that the force is equals to mx double dot, negative mx double dot. Okay, so the amplitude of a given value of force transmitted to the base is given by this equation. So basically you can rearrange the previous equation. Okay, previous equation we have it in terms of displacement. So now we make, instead of displacement, we can write it as in the form of force transmissibility. Okay, so you can get you can actually calculate the Ft to get the force transmitted. So now you have it, instead of x over y, now you have it in terms of force. So the equation is slightly different because you rearrange some of the terms. So if you plot the force transmitted force, so you can also see quite similar to the previous figure, but it's a little bit more refined, where you can see at r equals to root of 2. Okay, there is a deflection point there. So you have the value of transmitted force transmissibility. Okay, force transmissibility is basically, so the force transmissibility is actually TF, yeah, is actually very high. Okay, beyond this region when it's less than 2, but if it's more than 2, it also go somewhere higher along this line, okay, along the graph. Okay, and it is most of them are greater than 1. Okay, so you can see there is a slight difference, yeah. So let us take a look at example 1. So in this example, they give you a heavy machine, okay, supported on a resilient foundation. So basically they give you the parameters here, where you have 3000 Newton machine. So that will be your M basically. And then you have a foundation, you have a static deflection here. Okay, but now you have a base motion. Static deflection of the foundation due to the weight of the machine is 0.075 meter. Okay, and it is observed that the machine vibrates with an amplitude of 0.01. So this one is the output, which is a capital this one is y, this one is t, x. So this one would be your capital X, 0.01. when the base foundation is subject to harmonic oscillation at the undamped natural frequency of the system with an amplitude of 0.05. Okay, so you have your capital Y is equal to 0.0025 meter. So what you want to find is basically the damping constant of the foundation, which is C, and you want to find the force amplitude on the base, which is Ft, what is transmitted, and amplitude of displacement of the machine relative to the base, okay, which is your Z. So let us take a look at that. So you have the 3000, which is the M. You have static deflection, which is 0.0075 just now. Okay, I forgot to put the variable. Then you can calculate your K. After that, you can get your omega N. You can calculate your displacement transmissibility because they give both X, capital X, and capital Y. Then you can calculate at omega equals to omega N, you can calculate what is your zeta, the damping ratio. Okay, and as well from there, because you want to find damping coefficient, so you need to find zeta first. So you have the rest, then you can calculate your C. After that, they want you to calculate the force, the transmitted force. Okay, we already have the previous equation, which is this equation, the transmitted force. You can calculate from there. Since in this case, we already have the value of X and Y, so it's easy. You don't have to compute the rest of the thing all over again, because actually this expression here is represent X over Y, which is quite similar to this equation. Okay, so is X over Y is that whole expression. So that's how they use directly this equation. Yeah. So from there, you I also need the last part C. They want you to find the displacement of relative machine, which is your capital Z. So you have all the parameters you can substitute, which is actually 0.0097. So basically, hopefully you know the steps so that you can easily solve the problem. Okay, how do you actually determine the steps? Is basically you have to list out what are given variables and what are the things that you want to find, and take a look at the equations related to this topic, and then I'm sure you can understand, or you can proceed on the steps how you want to solve based on the equations one by one. So I guess that's all for this part. Okay, thank you very much. Bye.